Hello everyone, welcome to tutorial number 8. So we start with question number 1 where we want to prove that you take any simple graph G with 6 nodes, then either the complete graph K3 will be a subgraph of the graph G or the complete graph K3 will be a subgraph of the complement graph G complement. So let me first define what exactly is the complement of a graph in general. So the complement of a graph G is a graph which has the same vertex set as the vertex set G, and the edge set of G complement is complement of the edge set of the graph G. Namely, if you have an edge between the nodes Vi and Vj in the graph G, then the edge won't be present in G complement and vice versa, where Vi and Vj are distinct vertices. Okay, so that's a general definition of a complement of a graph, and we want to prove this property in any simple graph with 6 nodes. So if you see closely, then this question is equivalent to showing that the Ramsay number R33 or the Ramsay function R of 3 comma 3 is 6. Why so? So recall what exactly are the Ramsay numbers. So what here we want to prove that if you take any party where you have 6 guests, and if each pair of distinct individuals are either friends or enemies, then we prove that irrespective of the way the people are friends or enemies with each other, there always exist either three mutual friends, namely we can find three friends f1, f2, f3 who are mutually friends with each other. That means f1 and f2 are mutual friends, f2 and f3 are mutual friends, and f1 and f3 are mutual friends. Or we can always find three mutual enemies in the party. Okay, that means we can find three persons, person 1, person 2, person 3, such that P1 and P2 are not friends with each other, 2 and 3 are not friends with each other, and 1 and 3 are also not friends with each other. So we can model the friendship relation as an undirected graph, where I can say that there exists an edge between the person I and person J if and only if they are mutually friends. If we do that, then the friendship status of 6 people in a party, any party, can be represented by a simple graph with 6 nodes. And since we had proved that R of 3 comma 3 equal to 6, that is equivalent to showing this property that we are supposed to prove. We wanted to proving that R of 3 comma 3 is equal to 6 is equivalent to showing that if you take the friendship graph, you can always find three nodes in that friendship graph such that among those three nodes you have edges, right? So you can always find Vi, Vj, and Vk such that you have the edges between Vi, Vj, you have the edge between Vj and Vk, and you have the edge between Vk and Vi, or you have three people such that between I and j no edge is there, between j and k no edge is there, and between k and I no edge is there in the graph G. If no edges are there among these three nodes in the graph G, then in G complement graph you will have an edge between the edge nodes Vi and Vj, the nodes Vj and Vk, and the nodes Vk and Vk. So that is equivalent to showing that K3 is present, or K3 is a subgraph of the G complement graph. Right. So this question we have already solved in principle. It's just that we are now getting a graph theoretic interpretation of the friendship relationship. Now let us go to question number 2. Here we want to prove or disprove the following. If in a simple graph G minus Vi is disconnected for every vertex Vi in the graph, then it implies that the graph G is also disconnected. Or equivalently, here we want to check that if in the simple graph G, every vertex Vi is an articulation point or a cut vertex, then the graph G is disconnected. Because if G minus Vi is disconnected, that means the vertex Vi is an articulation point. So we want to check whether this property is true or not. To prove this, let us prove a related statement or a claim related or a claim related, or we prove a related claim. So the claim is the following. If you take any connected simple graph, then there always exist at least two vertices, none of which is an articulation point. This always holds in any connected simple graph. I can always guarantee the presence of uh, two vertices which are not cut vertices. Of course, the number of vertices in the graph is greater than equal to 2, because if the graph has just one vertex, then this claim does not make any sense. How exactly we prove this claim? So you focus on the nodes u comma v in the graph G, which are farthest. That means the distance among the nodes u and v is the maximum in the graph. That means you take all pair of nodes u comma v, find out the distance among those nodes u comma v, and among all the uv pairs, you focus on the uv pair such that the distance is maximum in the graph G. My claim is that the nodes u as well as the node v are not articulation point. They are not cut vertices. And this can be proved using a proof by contradiction. So on contrary, assume that, say, the vertex v is a cut vertex. So this is without loss of generality. The same argument can be applicable if we assume on contrary that the vertex u is a cut vertex. So if the vertex v is a cut vertex, that means by deleting the vertex v, my graph gets uh, divided into two connected components, C1 and C2. Okay, and this means that the vertex V has degree 2, and it will have at least one neighbor, say W, in the component C2. Right? Because if the degree of the vertex V would have been just 1, that means if the only neighbor of the vertex V would have been this vertex X in the component C1, and there is no neighbor W, right? Then how can it be possible that deleting V disconnects the graph or split the graph into two components C1 and C2? Since the deletion of V split your graph into two connected component, that means there is something, some node W in C2 such that V is having an edge to that node W in the connected component C2. Okay, but that gives you a contradiction to the fact that the nodes u and v are the farthest nodes in your graph G, because now you can see that the distance between the node u and w is more than the distance between the nodes u and v. That means my nodes u comma v are not the farthest nodes in the graph, but it's rather the nodes u and w which are the farthest nodes in the graph, right? So we get a contradiction, and that proves that whatever we assumed about the vertex v is not true. So we assume that the vertex v is a cut vertex, which is not true, right? So now coming back to the question is equivalent to saying that can we have a simple connected graph where every vertex is a cut vertex, right? And that is not possible, because that is precisely what we proved in this claim. We proved in this claim that if at all your graph is a connected simple graph, there are definitely, and the number of nodes is greater than equal to 2, then there definitely exist two vertices vi and vj such that neither vi is an articulation point nor vj is an articulation point, right? It's not possible. Right. Let us go to question number 3. So here we have to find an unknown graph G. The graph G is not given to you, but it's just given that it's a simple graph. And since the graph G is not known, we also don't know its incidence matrix B. But we know that the incidence matrix B is such that the product of the incidence matrix and its transpose is this matrix. So we have to basically recover the original graph G from the product of the incidence matrix and its transpose that is given to us. Of course, a naive way of doing that will be you try all possible values of, or all guesses of the B matrix and the B transpose matrix and multiply them and check whether your guess gives you this value of B into B transpose matrix or not. We won't do that. We will argue and try to get back the information regarding the graph G. Right? So imagine that your number of vertices in the graph is n and the number of edges in the graph is m. Right? So the incidence matrix of the unknown graph will be an n cross n matrix. Okay. So I am denoting the unknown incidence matrix by this notation. So B11, B12, B1M, they are the unknown Boolean values. Right. So remember each entry of the incidence matrix will be 0, 1, either 0 or 1. And if the edge E is between the vertex Vi and vertex Vj, then in the incidence matrix, if we focus on the eighth row, then under the column Vi, if we focus on the if we focus on the row number Vi and if we focus on the row number Vj and the column number E, then under the column E, in the ith row we will have the entry 1 and the jth entry we will have entry 1 and all other entries will be 0. That's a property of your incidence matrix. Okay. Now we don't know as of now which entries are 0, which entries are 1. Now it is easy to see that the jth row of the incidence matrix B will become the jth column in the transpose of the incidence matrix. And that comes from the property of the transpose of a matrix, right? And what will be the I comma jth entry when we multiply the matrix B with the matrix B transpose? So how exactly the I comma jth entry of the product of B and B transpose would be computed? We would have taken the ith row and we would have multiplied the ith row with the jth column component wise. Namely, bi1 would have been multiplied with b of j1 and then added to the product of bi2 and bj2, and like that we would have multiplied BIM, the entry number BIM, with the entry number BJM, and if we add all these things, that will give the I comma j entry of the matrix B into B transpose. And we are given the value of B into B transpose. So now what I can say is the following. If I take any I comma j entry where I is not equal to j, then the I comma j entry in the product matrix B into B transpose will be 1 if and only if the vertex Vi and the vertex Vj are incident on a common edge. That means they are the endpoints of an edge. This is because we already argued that this is our I comma jth entry. The I comma jth entry is 1 only if one of the values in this sum of m values is 1, because if none of the values in, so if the first product in this sum is 0 and if the second product in the sum is also 0 and like that if the mth product in the sum is also 0, then how come the I comma jth entry is of 1? So I comma jth entry is 1 only if you have bi1 equal to bj1 equal to 1. If that is the case, that means the vertex I and vertex j, they are the endpoints of the edge number 1. Or bi2 should be equal to bj2 should be equal to 1, which implies that the ith vertex and the jth vertex, they are the endpoints of the edge number 2 and so on. Right? So by focusing on the I comma jth entry where I and j are distinct and checking whether they are 1 or 0, we can identify whether the vertex vi and bj are the endpoints of an edge or not. And you have that information available in the product matrix B into B transpose. And if I take the I comma ith entry, right, that means if I substitute j equal to I here and focus on the I comma ith entry, then the I comma ith entry in the product matrix will be this expression, and this is nothing but the degree of the vertex vi. right? So you have all the information available now about the graph G from the product in the product matrix. So your graph G is such that the degree of 1 is 1, the degree of vertex 2 is 2, the degree of vertex 3 is 4, the degree of vertex number 4 is 2, and the degree of vertex number 5 is 3. And the endpoints of each edge is also available by focusing on the I, jth entry in this matrix where I and j are distinct. Right? So this is how you can get back all the information about your unknown graph from the product matrix P into B transpose. Right. So now let us go to question number 4. In question number 4, we have given the definition of a tree. So tree is a connected acyclic graph. That means it is a graph which is connected. That means you take every pair of distinct nodes, there will be a path, and it is acyclic. That means the graph has no cycle. We have to show that if you take any tree with n nodes, then the tree has n minus 1 edges. Okay. So there are several ways to prove this theorem. We will use a proof by induction on the number of nodes n. So it is obviously true, the statement is obviously true for the base case, namely for a tree which has only one node. So if you take a tree with one node, then it will have 0 edges. Assume the inductive hypothesis is true. That means assume the statement is true for all trees consisting of up to k nodes. And now we are going to the inductive step where we are going to consider an arbitrary tree consisting of k plus 1 nodes, and we focus on any arbitrary edge with endpoints u and v in the graph G or the tree G. My claim is that the edge u comma v is a cut edge in the tree, and this is true for any edge in the tree. You take any edge, the claim is it will be a cut edge, right? That means if you remove the edge connecting the nodes u and v, then your tree G gets splitted or divided into two connected components. If that is not the case, that means even if after deleting the edge between u and v, your tree remains connected, that means there is still some way to get back to the node u from the vertex u. Even if this edge is not there between u and v, then we get the conclusion that there is a cycle in the graph, but that goes against the definition of a tree, right? So now, if my edge u comma v is a cut edge, I will get two components C1 and C2. I don't know how many nodes are there in C1 and how many nodes are there in C2. So I can assume that they have n1 and n2 number of nodes respectively. But what I know is that if I sum up the nodes, number of nodes in C1 and the number of nodes in C2, that will give me the total number of nodes that I have in the tree, which is k plus 1. And I also know that both n1 as well as n2 is upper bounded by k. This is because C1 and C2 are disjoint, right? And both of them are non-empty. So since n1 and n2 is less than equal to k, and both C1 is connected as well as C2 is connected, and I don't have any cycle in C1 and I don't have a cycle in C2, that means both C1 as well as C2 are individually trees with n1 and n2 nodes respectively. So as per the inductive hypothesis, I can apply the inductive hypothesis and claim that the number of edges in C1 is n1 minus 1, the number of edges in C2 is n2 minus 1, and that gives me that that tells me that the total number of edges in the original tree G is just one more than the number of edges that I have in the tree C1 and C2. This is because the only edge which I have touched or removed is the edge between the nodes U and V, and that proves the inductive step. Okay, right. So now let's go to question number 5. In question number 5, we define what we call a self-complementary graph. So a graph G is called self-complementary if it is isomorphic to its complement. So for instance, this is a self-complementary graph with 4 nodes, right? So I'm not labeling the nodes, but you can check here that the graph G and the graph G complement, they are isomorphic to each other, and hence the graph G is self-complementary here. So we want to prove here a very interesting property about self-complementary graphs. We want to prove that if your graph is a self-complementary graph, then the number of nodes in the graph is either a multiple of 4 or it is some 4 times k plus 1. That means either the number of vertices is completely divisible by 4, or if you divide the number of vertices by 4, then you will get the remainder 1. That is what we want to prove here. At least you can check that this statement is true for the G and G prime that we have here. The number of vertices in G is 4 and 4 is divisible by 4. So how do we prove this? So since the graph G is self-complementary, that means the number of edges in G and the number of edges in G complement have to be same. So the cardinality of the edge set E and the edge set E complement will be same. And I know that for any graph, it need not be self-complementary. If you take any graph, then the total number of edges in E and E complement is same as the product of the number of vertices and the number of vertices minus 1 over 2, right? Because all the edges which are in G, they won't be in G complement and vice versa. And if you take the union of the graph G and the graph G complement, you will get a complete graph with the number of nodes same as the number of vertices in the graph G or G complement, right? So if you take G union G complement, then you get the complete graph with n nodes, where n is the number of vertices, okay, in the graph G. So remember, the number of vertices in G and G complement will remain the same. You don't take complement with respect to the vertex set. The complement is with respect to the edge set. Okay, so we know these two facts. One fact that is true for every self-complementary graph and another fact which is true for every graph. Based on these two things, if I substitute that cardinality of E is same as cardinality of E complement, then I get that 2 times the cardinality of E is equal to this quantity, which shows that the product of the cardinality of the vertex set and the vertex set minus 1 is a multiple of 4, right? Or it is divisible by 4. Now you have two quantities here, A and B. Okay, and what are the prime factors of 4? 2 and 2. It turns out that you can't have both A as well as B simultaneously divisible by 2, because one of the quantities is odd then the other quantity will be even, right? A and B you can't have two consecutive numbers, both of them simultaneously divisible by 2, and that, but since I know that the product of A into B is divisible by 4, then that is possible only if either A is divisible by 4 or B is divisible by 4, right? If both A and B would have been individually divisible by 2, then I can't claim this fact here. But since I know that both A and B cannot be simultaneously divisible by 2, but the overall product A times B is divisible by 4, then that is possible only if A times B is divisible by 4, only when either A is divisible by 4 or B is divisible by 4, right? And that shows what we wanted to prove here. Okay, right. Now, in the same question, we want to draw a self-complementary graph uh, with a vertex set which has 4k number of nodes, right? So you are given a value k could be anything, k could be 1, 2, 3, 4. Given the value of k, you have to draw a self-complementary graph which has 4 times k number of nodes. So if k is equal to 1, then this is the self-complementary graph, but you can't draw a distinct self-complementary graph for each and every value of k. I just want to draw a general graph, right, which unifies all self-complementary graphs with 4k number of nodes. So how do we do that? So what I do here is I take 4 groups of k nodes, and those 4 groups of k nodes are disjoint. So this is my first group, this is my second group, this is my third group, and this is my fourth group. Okay, now this group of k nodes denotes a complete graph with k nodes. That means you have edge between every pair of distinct nodes in this group. And similarly, this copy of k nodes denotes a complete graph with k nodes. And this group, H complement, denotes an incomplete graph of k node. That means it's a collection of k nodes with 0 edges. And similarly, this collection of k nodes have 0 edges. Okay. Now what I do is the following. My G is the following. My graph G, which is a self-complementary graph with 4k nodes, is the following. So of course my graph G will be now having 4k nodes because the total number of nodes are k plus k plus k plus k, so 4k nodes. Now what I am doing here is the following. So this thick edge between this group of k nodes and this group of k nodes denotes that if you have the nodes v1 to vk here, and if you have the nodes v of k plus 1 to v of 2k here, this collection, then you have an edge between every node in this group and every node in this group. That's what is the interpretation of this thick edge. Similarly, you have an edge between every group in between every node in this group and every node in this group. That's the interpretation of this thick edge. And similarly, you have an edge between every vertex in this group and every vertex in this group. That's interpreted by this thick edge. That's the interpretation of this thick edge. Okay. So that's my graph G. Okay. Now what will be the complement of this graph G? So this is my graph G. So my graph G complement will also have 4k number of nodes. But then what will happen is the following. So since this group was a group of k nodes with edges between every pair of nodes, you will still have those k nodes but no edges among any pair of nodes. Whereas this copy of k nodes will get converted into a complete graph of k nodes. This copy of a complete graph of k nodes will get converted into a collection of k nodes with no edges, and this copy of a graph with k nodes and 0 edges gets converted into a complete graph with k nodes. And then since these edges were present in G, they won't be present here anymore. Right? So that's why these edges have vanished. And similarly, you can see the edges which were not there in G, they will be now present in G complement, and vice versa. The edges which were not there in G, they will be present in G complement. So there were no edges between this group and this group in G, but now those edges are here, and so on. So, right? So that's how your G complement will look like. So it is easy to see that your graph G complement is isomorphic to the graph G, right? I can interpret or rearrange or redraw the graph G complement in the same form as the graph G, right? I just have to orient it a little bit. That's all, right? So if I orient this graph, rotate this graph little bit like this, then I get the same structure as the graph G, and that shows that my graph G and G is self-complementary because it is isomorphic to its own complement. In question 6, we have to either prove or disprove the following. If the graph H is a subgraph of G, then can we say that H complement is also a subgraph of G complement? Well, the statement is not necessarily true. A very simple counter example is the following. Here you have a graph H and a graph G. The graph H is a subgraph of G, but if you take H complement, in H complement, the only edge will be between the nodes 1 and 3 because the edge between 1 and 3 was not there. Whereas in G complement, there won't be any edge. So clearly, H prime or the graph H complement is not a subgraph of the graph G complement, right? So this statement is not necessarily true. Then let's see question number 7 and 8. A simple graph is called regular if the degree of every vertex is same. And if the degree of every vertex in a simple graph is some value r, then we call such a graph as R regular graph. Okay. So here you are given few graphs and we have to find out which of these graphs are regular and which are not. So Kn is a regular graph because the complete graph with n nodes, in such a graph, the degree of every vertex is n minus 1, so it is regular. The cycle graph with n nodes is also regular because you take the degree of every vertex, it will be 2. But your wheel graph W of n is not a regular graph because it is the central node which has a huge degree compared to the other vertices of the graph, right? Whereas if you take the hypercube graph, we can prove that it is a regular graph. The degree of every vertex will be the same. Okay. Now, what we have to do in question 8 is the following. You are given a value of k. Given the value of k, you have to draw a simple regular graph where the degree of every vertex is 2 times k plus 1 such that the graph has a cut edge. Okay. You have to give the construction of a general graph. So what we can do here is the following. We take 2 copies of a complete bipartite graph, right? So we take 1 copy of a complete bipartite graph where I have 2k nodes in the individual sets in the bipartition. So 2k number of nodes in V1 and 2k number of nodes in V2, and I have an edge between every vertex in V1 and every vertex in V2 that is denoted by this arrow symbol. Okay, by implication symbol, because the graph will look very ugly if I keep on adding edges between every vertex in V1 and every vertex in V2. So to avoid making it looking ugly, I just denote the existence of an edge between every node in V1 and every node in V2 by this by implication. And similarly, I take another copy of a complete bipartite graph and say I call the bipartition of this copy of the complete bipartite graph as V1 prime and V2 prime. And again, I have an edge between every node in V1 prime and every node in V2 prime. Okay. So this is my V1, V2, V1 prime, V2 prime. Now I need to ensure that my graph has a cut edge. So I try to introduce a cut edge. So this will be my overall cut edge. And what I do here is, so let me call the endpoints of this cut edge as A and B. I connect the node A to every vertex in the subset V2. Okay. So that will ensure that the degree of the vertex A is 2k plus 1. Why 2k plus 1? Because it will be connected to all the vertices of V2. So it gets degree 2k through that. And it's also having an edge to the node V. Incident. So it is a neighbor of the node B. So that ensures that the degree of A is 2k plus 1. Using the similar argument, I can say that the degree of B is also 2k plus 1 because it is neighbor. B will have a neighbor with B has a neighbor in every vertex with V in V1 prime. So through that it gets 2k degree, and B is also a neighbor of the node A. So an additional degree. So the degree of B is also 2k plus 1. Okay. Now all the vertices of V2 will have degree 2k plus 1. This is because you take any vertex of V2, say the first vertex. So it is neighbor of A, so get degree 1, and it is having an edge with every node in V1. So through that it gets the degree 2k. So total degree 2k plus 1, right? Due to the same argument, each node in V1 prime also have degree 2k plus 1 because you take any node in V1 prime, it is having an edge with every node in V2 prime. So through that it gets degree 2k, and the same node is also having an edge with the node B. So through that it gets one more degree. So total degree 2k plus 1. But we also need to ensure that every vertex in V1 and every vertex in V2 prime uh, also gets degree 2k plus 1. Okay. So till now we have ensured that the degree of A is 2k plus 1. We have ensured that the degree of B is 2k plus 1. We have ensured that every vertex in V2 has degree 2k plus 1. And we have ensured that every vertex in V1 prime has degree 2k plus 1. But right now the degree of every vertex in V1 is 2k, right? And similarly the degree of every vertex in V2 prime is 2k. I need to increase the degree of each vertex in V1 by 1, and I have to increase the degree of each vertex in V2 prime by 1 as well. And that is simple. What we can do is the following. You take the vertex set V1, you pair them into k pairs. You take the first two nodes and add an edge between them. Then you take the third and the fourth node and add an edge between them. And like that you take the fifth and the sixth node and add an edge between them, and so on. So that will ensure that the degree of every vertex in V1 becomes 2k plus 1. And if you do the similar process for V2 prime as well, that will ensure that the degree of every vertex in V2 prime becomes 2k plus 1. So with that, I conclude tutorial number 8. Thank you.